You've definitely seen it hanging on a classroom wall, but have you ever really looked at the periodic table and wondered, why is it shaped like that? Well, it's not random at all. It's actually a secret code, a map to the entire chemical universe. And today, we're going to crack it.
To get why this is so brilliant, first you have to imagine total chaos. Picture walking into a gigantic library where all the books are just thrown into piles. No system, no order. Good luck finding anything, right? It would be an absolute nightmare.
Well, that's exactly the problem chemists had a long time ago. They had all these unique elements. You're talking explosive metals, invisible gases, you name it, and each one had its own special personality. How on earth do you bring order to all of that chemical chaos?
And look, this wasn't just about being neat and tidy. This was one of the biggest mysteries in all of chemistry. If you could solve this puzzle, you could unlock the fundamental secrets of matter itself.
So here's the dilemma they were facing. You've got over 100 elements, and they all behave in their own weird ways. Trying to memorize everything was just impossible, and figuring out how they might react together, that was pure guesswork. Science desperately needed a system, some kind of pattern. And then, a breakthrough, a huge one. Scientists figured out there was a single beautiful rule, a kind of universal secret code that could take that messy, chaotic library of chemicals and turn it into a perfectly organized system.
And this is it. This is the code, the modern periodic law. Now, it says that the properties of elements are periodic functions of their atomic numbers. I know, that sounds a little technical, but the idea behind it is incredibly simple. It all boils down to one number. How many protons are in an atom's core? That one number dictates everything.
So what's a periodic function? It's just a fancy way of saying a pattern that repeats itself. I mean, think about the days of the week. You go through Monday, Tuesday, all the way to Sunday, and then what happens? Of course, Monday comes right back around. The periodic table does the exact same thing. As you line up the elements by their atomic number, their properties start repeating in a predictable cycle.
This repeating pattern, that's the absolute key. It lets us predict how an element is going to act, just by looking at where it lives on the map. So let's start decoding some of these amazing patterns, or what we call trends.
First up is size, or what chemists call the atomic radius. It's really simple. It's just the distance from the very center of an atom, the nucleus, all the way out to its most distant layer of electrons. Basically, how big is the atom?
And this is where the patterns get really cool and a little weird. You'd probably think that as you move from left to right across the table, adding more stuff, the atoms would get bigger. But nope, they actually get smaller. That's because the nucleus is getting stronger and it pulls all those electrons in tighter. But as you go down a column, the atoms do get bigger, just like you'd expect. So what's going on there?
Well, it's because every time you move down a row, you're adding a whole new layer, a brand new shell of electrons. Just think of it like an onion. Every time you add another layer, the whole onion gets bigger. It's really that simple.
Things get even more interesting when atoms become ions by gaining or losing electrons. So if an atom loses an electron, it becomes a positive ion, called a cation, and it actually shrinks. But if it grabs an extra electron, becoming a negative anion, it puffs up and expands.
Okay, let's look at our next trend, which is tied directly to size. It's called ionization energy. The easiest way to think about this is as an atom's grip strength. It's how much energy you need to use to snatch one of its electrons away. A really high ionization energy means that atom has a super tight grip. Here's an analogy. Imagine someone is swinging a stone on a string. If that string is really short, the stone is zipping around and it's going to be really hard to grab. But if the string is long, it's way easier. It's the same idea with atoms. For bigger atoms, those outer electrons are on a longer string, and they're just easier to pluck off.
So we've got these patterns of size and grip strength. But why does any of this matter? Well, it matters because these trends directly control how elements actually behave in the real world. So let's see them in action.
You can think of the periodic table like a big city map that's divided up into different neighborhoods, or what we call blocks. And each of these neighborhoods has its own unique vibe, all based on how their electrons are arranged.
All right, let's take a quick tour. Over on the left, you've got the S block, home to some super reactive metals. On the right is the P block, which is the most diverse neighborhood. It's got a mix of everything. In the middle, you have the D block, with all the hard-working transition metals like iron and copper. And that little section at the bottom, the F block, That's where you'll find the heavy hitters used in nuclear science.
And this is where it all clicks into place. For metals, being reactive means being able to lose an electron easily. And since atoms get bigger as you go down a group, that outermost electron is further away and easier to give up. So, reactivity goes up. For nonmetals, it's the total opposite. They want to gain an electron, so the strongest pull wins. That means reactivity increases as you go up a group.
And what about that very last column all the way on the right? Aha, the noble gases. These are the VIPs of the table. They already have a full outer shell of electrons, which is basically the goal for every atom. They're stable, they're happy, and they have almost zero interest in reacting with anything else. So, when you put this all together, the structure, the repeating trends, the neighborhoods, you start to see the real genius of the periodic table. It all comes down to its unbelievable predictive power. It takes chemistry from being this huge list of random facts you have to memorize and turns it into a logical, predictable science. It's so much more than a chart.
It's a powerful map that lets us navigate and truly understand the building blocks of, well, everything.
And what's absolutely mind-blowing is that this predictive power is real. The original creator of the table, Mendeleev, actually left empty spaces in his chart, predicting the existence and the properties of elements years before anyone ever found them. So this map doesn't just show us what we know, it shows us what's still out there, which leaves us with a pretty cool question. Based on these very same patterns, what can we predict about the next element that we discover?